So ladies and gentlemen, welcome. Today we're going to talk about throughput manipulation. Throughput is synonymous with processing rate, feed processing rate or production rate. And every process must produce as per market demand, as told by the business, the management. So your production could be high in high demand season and production could be low in low demand seasons. And in order to increase or decrease production, there is a particular set point that will be increased or decreased, which is like the gas pedal in a car or a motorcycle. So the throughput manipulator is the set point that gets adjusted to bring about a change in the production rate or processing rate. The production rate or processing rate is also known as the throughput. In front of you got 3 units in series, connected in series. Unit 1 is feeding into unit 2, unit 2 is feeding into unit 3. You got a feed into unit 1 and you got the product coming out of unit 3. Typically the control system would be structured as the fresh feed will be fixed and the inventory control system downstream of the fresh feed would be in the direction of flow. So the level controllers will be oriented in the direction of flow and they are there in front of you. If you want to bring about a change in the production, the operator will change this feed rate in order to bring a change in production. And as we have seen in the previous lecture, where you are fixing feed, the flow would be calm there, and as you go further downstream, flow variability will increase due to the action of the level controller and also disturbances entering unit 1, unit 2 and unit 3. So the variability in the flow will typically increase as you go downstream. And now imagine a situation where you want to maximize production and unit 3, the star here indicates that this is the bottleneck unit. In any process, if you want to maximize production, there will be one unit that will reach maximum capacity. There's an old saying in English, the chain is only as strong as the weakest link. So if you want to maximize production, this is your weakest link, unit 3. Unit 3 reaches its maximum capacity quickest, and so it starts raising its hand. Whoa, I can't handle anymore. I have reached my maximum capacity. So now imagine a control system that is like this, and the management says maximize production, the market scenario is good. So the feed to unit 3 cannot exceed a certain maximum, and I'm showing you that as a red line, because if the feed goes beyond this red line, there will be hydraulic problems, all kinds of problems, safety issues, I don't know, and because of that you will have to take unit 3 offline and bring it back online, and that will be lost production. So to maintain safe, stable operation, you have this hard limit, this red limit, which cannot be exceeded. So because this red limit cannot be exceeded, what the operator would do is choose this throughput manipulator set point such that even with the variability in the flow going into unit 3, that red hard limit is never exceeded. And note that unit 3 is actually capable of operating at the red line all the time, but because of the variability in the flow going into the unit 3, the average operation is below the red line, and so the hashed area is lost production. You could have operated at the red limit, but you are operating below that, and therefore the hashed area is lost production. Now given that you know that unit 3 is the bottleneck, and if you structure the control system the way it is structured right now, you're going to end up losing production corresponding to the magenta hashed lines shown there. What you can then choose is, if you know that unit 3 is the bottleneck, you can choose to hold the flow to unit 3 constant. You can choose to locate your throughput manipulator at the bottleneck, and now the calmest place in the tank in the unit would be the flow into unit 3, and now you can set the set point at the red limit, and therefore there is no lost production. And as you move away from the bottleneck, there's variability in flow, but at the bottleneck the flow variability is as small as can be, and therefore you can operate at the bottleneck limit, and therefore the production loss is negligible, zero, least. Okay, so what have we learned from this? Well, if you know where the bottleneck is, it's always a good idea to choose the throughput manipulator at the bottleneck and then propagate variability away from the bottleneck. You see, this is the bottleneck, and the way the level controllers are oriented, upstream level controllers are oriented in the reverse direction of flow, downstream level controllers are oriented in the direction of flow. So the orientation of the inventory control system is to propagate transients away from the bottleneck, and that allows us to operate at the bottleneck limit. Okay. So with respect to throughput manipulator selection, what can we say? If the throughput manipulator choice is flexible, and when is the throughput manipulator choice flexible? When you've got these large storage tanks supplying fresh feed into a plant. You can change the feed rate as much as you want, because the storage tank itself is large. There will be a slight change in the level. And when you have such large storage tanks supplying fresh feed, variability in the storage tank level is acceptable. This will allow structures, control structures, that can be structured in a manner that bring the fresh feed in as makeup streams. You know, the transformation of variability from the recycle loop into the feed. Those kind of structures are usually possible when you have large storage tanks supplying fresh feeds. Usually plant designs have large recycle rates for economic reasons, and so the design is almost always in the snowballing region. And when the design is in the snowballing region, you increase the production a little bit, the recycle rate increases a lot, and therefore the capacity bottleneck, the unit that reaches its processing limit, that capacity bottleneck is usually inside the recycle loop, because the recycle flows blow up much faster than the flows outside the recycle loop because of snowballing, which we talked about earlier. So the capacity bottleneck then is likely inside the recycle loop. Given all of this, where to locate the throughput manipulator? If you know nothing about the process, put it in the recycle loop. So what will that do is it will keep the flow in the recycle loop relatively constant, so the variability going into the bottleneck in the recycle loop will be mitigated, even though you may not know where the bottleneck is. This also avoids those other issues of infeasibility, set point infeasibility, faster dynamics, because it is the recycle loop, recycle flow that you're directly fixing, and not fixing a fresh feed and expecting the recycle to float to the appropriate value that it has to float to, which can take a long time. If there are multiple recycle loops in a process, then you place the throughput manipulator on a common branch. So that will do is it will sort of regulate the flow variability in both the loops, because you have fixed the flow in the common branch. Of course, if the bottleneck is known, then you should choose the throughput manipulator at the bottleneck constraint, and once your throughput manipulator is chosen, beyond that fix your throughput manipulator and then start designing the level controllers and the pressure controllers and the temperature controllers around that bottleneck. So once the bottleneck the throughput manipulator location is fixed, the inventory control system gets designed around it. Where to choose the throughput manipulator? Definitely inside the recycle loop. If you know nothing about the process, there are multiple recycle loops, you put the throughput manipulator on a common branch to the two recycle loops. If the bottleneck is known, and usually the bottleneck will be inside the recycle loop, you choose the throughput manipulator at the bottleneck constraint. That's the key understanding that comes from this simple argument, these simple arguments. Now let's revisit what we have learned over the last 2 or 3 lectures. The key plant-wide control guideline is that you need to configure the control system to transform recycle rate variability out of the recycle loop, whether it's a material recycle loop or an energy recycle loop. Bottom line, energy balance variability needs to be transformed out of the energy recycle loop. Material balance variability needs to be transformed out of the material recycle loop. The plant should be such that there are control degrees of freedom that allow fast local control. What do I mean by local control? That means if you want to control a process variable in a unit, there is a manipulation handle in the unit that gives tight control for that. The degree of freedom is not far away, so the dynamics is going to be slow, and therefore the control is going to be loose. The degree of freedom for control is close by, it's local to the unit. And then you pair locally for fast control. Because the pairing is local, the dynamics is fast. Because the dynamics is fast, the control can be tight. And last but not least, you choose the throughput manipulator at the bottleneck constraint to transform variability away from the bottleneck, and this will automatically bring in the fresh feed as a makeup stream because the bottleneck is inside the recycle loop. Almost always the bottleneck is inside the recycle loop. These are the key plant-wide control guidelines that emerge from all that we have done in the last 2 or 3 lectures. Now let's just start applying this to our toy process. Exercise 1. This is the same A plus B goes to C process. I don't need to talk about it. Explain to you. Steady state degrees of freedom is 6. Control degrees of freedom is 9. 2 level controllers with no effect on steady state on the column. Column operates at given pressure. That takes away 3 degrees of freedom. That leaves us 6 steady state degrees of freedom. Let's say you have a conventional control structure where the throughput manipulator is at a fresh feed. We are saying it is at the fresh B feed. So this is your throughput manipulator. Now because A plus B goes to C, for every mole of B that you are putting in, you got to put 1 mole of A. So you got A coming in under ratio control, and the ratio is with respect to the A feed rate. On the reactor you got temperature control to close the energy balance, you got level control to close the material balance on the reactor. On the column you got standard level controllers, up and down, pressure controller, and then you got reflux under flow control and bottom quality being controlled by holding a tray temperature, inferentially controlled by holding a tray temperature, and the tray temperature controller manipulates the reboiler duty. So this is a standard control structure. Of course you need this composition control, because without the composition controller, suppose you don't have the composition controller, then you could have a slight excess of A or a slight excess of B, because the flow measurements are not exact, and whichever reactant is in slight excess, it will not have the other reactant to react with. So, and the temperature controller here does not allow the either A or B to drop down the column. So whichever component is in excess, that will keep building up in the recycle loop, and therefore this build up in the recycle loop is prevented by this composition controller. It will reflect in whichever component is excess, its composition building and the composition of the other reactant decreasing. So you hold the composition of a reactant in the reactor by adjusting the the A to B reactant ratio, and with this you have no drifting modes. All balances, material and energy, are closed properly. This is a proper control system, a consistent control system that closes all balances. Alright. The point is, the composition control, the need for composition control is not very obvious to many people, and without that composition control there is the possibility of stoichiometric imbalance, and that stoichiometric imbalance will cause a slow, subtle drift in the excess reactant A or B in the recycle loop. And so there are always these possible subtle recycle loop inventory drifts that are possible, and so you got to be careful and identify and be doubly sure that the material balance, particularly the overall material balance on the plant, is fully closed. Also note that plant-wide balances close slowly due to recycle, and in order to be aware that all balances are being closed and there are no subtle drifting modes like the one we have in this simple process, it is always a good idea to examine the process input-output structure and ensure that every component that is being put in either has a way out or gets consumed by reaction. This is called Downs drill. The person who proposed it was Jim Downs. And in this particular example, you got A being recycled, B being recycled, you got fresh A coming in, fresh B coming in. Because the product is near pure C with very little A impurity and B impurity, therefore because the reaction chemistry is A reacts with B to give C, 1 mole of A reacts with 1 mole of B to give C, and you are taking out only C. Therefore, if you are putting in 1 mole of A, you got to put in 1 mole of B exactly. And because this is never exact, what is done is some kind of inventory controller, and in the example that we have, we are using a reactor composition controller. The fresh B is being brought in under inventory control. A is maintained in ratio with B, and that ratio is adjusted by this composition controller, the inventory controller, so that B exactly matches A. You cannot independently set this, that's the point. And that comes from the overall material balance structure of the process. Okay. We've seen this before. There are always two options. You could fix the fresh flow, and the recycle and the product flow would be under inventory control, some kind of level control, pressure control. Or you could fix a recycle flow and bring in the fresh feed under inventory control and take out the product under inventory control, and the latter is always a good idea. We've argued about this earlier, but it is good to remind ourselves of this. And then continue. So this control structure where throughput manipulator is at the fresh B feed. Now we ask the next question, how do we set the other set points so that the operation is optimal? Well, obviously the temperature should be the maximum, so that the reactor single pass conversion is the maximum. If the reactor single pass conversion is the maximum, the recycle load would be the minimum, and that would minimize the amount of steam that I am putting in the reboiler. That would minimize my energy consumed for the given production rate. For similar reasons, the reactor level should also be maximum. The temperature controller should have the least minimum possible set point, so that the purity of the product is at the quality guarantee that you're giving. So if the quality guarantee is 99 mole% pure product, then the purity of the product should be exactly 99 mole%, not 99.5, because then you're selling 0.5% product for free. So to minimize free product giveaway, the temperature controller or the composition of the product should be at the minimum guarantee for the customer. That is what determines the set point of the temperature controller, and that is what this minimum here indicates. So there are 6 set points: the composition control set point, the reflux set point, and the other 4 set points. Of these 6 set points, 4 are either given or set at maximum or minimum based on economic considerations. This leaves us with these 2 set points. How should we be setting these 2 set points? We'll talk about this also later. But the point is, if there are 6 degrees of freedom, 4 of them get taken away by simple common sense arguments. Production is given, reactor temperature should be maximum, reactor level should be maximum, and the product quality should be minimum. So that takes away 4 degrees of freedom. You are left with only 2 set points that you need to manage. Okay. How to manage those 2 unconstrained set points, those 2 question marks? That's another story for another day. We'll talk about that later. Sometimes what happens is, for example, in utility plants, the throughput manipulator has to be on the product stream. Utility plants, for example, a boiler house generating steam for so many downstream processes. If a downstream process says give me more steam, immediately more steam has to be given. Same thing with electricity. If you put on your iron, you want current to be supplied immediately to the iron. It cannot be that the current will get supplied 5 minutes, 15 minutes, 20 minutes down the line. It has to be immediate. So whatever is demanded, that demand has to be immediately met. So then you have to have the throughput manipulator on the product stream, and the throughput, this set point is being set by the user. And now that the throughput manipulator is at the product stream, level control will have to be this way, temperature control will have to be that way, level control will have to be that way, everything else is the same. Of course, optimal operation would be same thing, level should be maximum, reactor temperature should be maximum. And then again you are left with these 2 set points that are unconstrained. How do we choose their values? Yeah. So this is another possible control structure for on-demand operation. Both of these structures will give the previous structure, and this structure will close all the material and energy balances. It's just that that structure was different, this structure is different, that structure was process the given feed, this structure is on demand operation, give customer whatever is demanding immediately. You could also have the throughput manipulator as fixing the total flow to the reactor, and everything else is the same. Max, min, unknowns, unconstrained set points. This is another possible control structure. You could also have when the throughput manipulator location is flexible, and let us say the bottleneck unit is flooding in the column. When you want to maximize production, the column floods. What do you mean by flooding? The vapor rate in the column is so high that it starts entraining liquid from a tray and carrying it to the upward tray, to the tray above it, and so there is liquid back mixing, and that drastically adversely affects the separation efficiency. Your distillate starts becoming impure, your bottom starts becoming impure, and so this entrainment flooding is because of too high a vapor rate, and that is usually reflected as, when the vapor rate is too high, that will be reflected as large pressure drop across the column. And so what is typically done is you hold the pressure drop across the column at a maximum value so that that pressure drop limits the boil up. But in our example, we'll just say that we know what is the maximum boil up that you can handle, and the throughput manipulator will be set at that maximum, so that because boil up is the bottleneck constraint, we will use the throughput manipulator as the boil up, and the boil up comes from the steam here. So the throughput manipulator is on the steam valve to the column, steam valve to the reboiler, and we are setting it up here because we know that it is maximum boil up, that is the bottleneck. Now if the throughput manipulator is here, column temperature cannot be controlled this way, so the column temperature will have to be controlled using the fresh feed. That's exactly what we do. Level control is this way, level control on the reactor is that way, everything else is the same as before. You've got the same maxes and the minimas, and then you've got these same unconstrained set points which we don't know what their value should be, and we'll try and find them out systematically. Now if you want to maximize throughput and column pressure drop reaching a maximum limit is the bottleneck, if the control structure is the conventional one where the throughput manipulator is at the fresh B feed, there what will the operator do? Operator will see, okay, what is the delta P in the column? If the delta P is sufficiently below the maximum limit, he will increase the fresh P going into the process. So what he's essentially doing is, in order to hold the delta P constant, he is adjusting the fresh P feed rate. This loop, however, is long. You would like this to be at max, the delta P should be at max for maximum production rate, but however the loop is long, dynamics is going to be very slow. Because the dynamics is slow, the control cannot be as tight, and therefore because of this long loop you will have a large back off, because the delta P max, this max limit cannot be breached. So if this is the black line is the variability in the delta P, you must make sure that the maximum in the delta P does not breach the red line, and therefore your average operation is going to be substantially below the max limit. So your set point will have, the set point to the delta P loop will have substantial back off, large back off. So you have large loss production. If you have on demand structure and the column flooding is your bottleneck, then what you would be doing is doing this, and here too you will need a backup. Everything else is the same. However, the backup is going to be not very large, because you change the throughput manipulator, you change this flow, the level will change. As soon as the level changes, the level controller will change the steam rate. As soon as the steam rate changes, the boil up changes. So the variability in the boil up is sort of not immediate, but the dynamics is not very slow. Okay, so because the dynamics is reasonably fast, you could have reasonably tight control, and because you have reasonably tight control of delta P using this magenta loop, therefore the backup is not going to be large. There's going to be some backup, but it is going to be much lower compared to the previous control structure. If you use this, again it's going to be a long loop. However, since you are holding the total flow here, so the variability in the flow going into the column is going to be less, because the variability in the flow going into the column is going to be less. Back off is likely to be lower than if you're fixing the fresh feed. That's because you're guarding against snowballing. The most interesting case is here when you're choosing the throughput manipulator at the bottleneck. In this case, what we will do is we will hold the delta P across the column by adjusting the steam to the column, and you adjust the steam to the column, boil up immediately changes. It's instantaneous or very fast open loop dynamics. So the control can be made very tight, and because the control can be made very tight, therefore the variability in the boil up can be made very small. Because the variability in the boil up because of tight control can be made very small, you can operate very close to the maximum limit, and then the delta, the back off, is negligible. So in this case you will be able to operate the column very close to its flooding limit without breaching the flooding limit, and therefore this control structure will give you much higher production compared to the previous control structures. Yeah. So now I would like to summarize the plant-wide control system design steps. First step is always degrees of freedom analysis and seeing what are your control objectives. Control objectives are always, you got to have control of the production rate, you got to have tight quality control, you may also have safety limits. For example, if there's oxygen, ethylene oxide is made by reacting ethylene with oxygen. Ethylene and oxygen can explode. Yeah, so there are flammability limits. If the composition is between the upper flammability limit and the lower flammability limit, then the mixture will burn, can burn. Put in a spark, the mixture can burn. Upper flammability limit is there's too much fuel, there's too little oxygen. Lower flammability limit is there's too little fuel, so fire won't go. But if you're in the right range, so oxygen starved, fuel starved, these are the two limits. If you are neither oxygen starved nor fuel starved, a fire can happen, an explosion can happen, and so sometimes there are safety limits. Safety also dictates that all inventories be controlled, all material and energy balances be closed, and then there are of course economic considerations that dictate what should be the set point of these inventory controllers. Okay, so all this is part of degrees of freedom analysis and control objectives. Also part of degrees of freedom and analysis and control objectives is what to control. When I control, those question marks that were there, the set points, the composition set point of the reactor and the reflux rate, what should these set points be so that my operation is optimal? Alternatively, what variable may I control by adjusting the reaction composition, the reactor composition controller set point may be adjusted to hold what magic variable constant such that my steam consumption in the reactor is minimum per kg product. So you also have these economic considerations that translate into what to control, what can we control, so that these unconstrained degrees of freedom that are not at their maximum or minimum limits, these unconstrained degrees of freedom are managed in a near optimal manner. Yeah, so that's all of that is part of this analysis, degrees of freedom analysis and control objectives. Once you know what to control, what are your control objectives, the inventory control objectives, safety, product quality, production rate, etc., then the next thing that you do is choose the throughput manipulator. In some plants, the throughput may be set by an upstream process, in which case the throughput manipulator is the fresh feed. Whatever is being given by the upstream process, you got to process that. In some plants, you got to have on-demand operation, for example, utility plants, in which case the throughput manipulator is at the product. Many a times, the throughput manipulator location is flexible. If it is flexible, because you got supply from a large storage tank, fresh feed being supplied from large storage tank farms, then the throughput manipulator should be inside the recycle loop at the feed of the most non-linear or fragile unit. If you don't know where the bottleneck is, if the bottleneck is known, usually that bottleneck will be inside the recycle loop, and then what we are saying is you choose the throughput manipulator at the bottleneck inside the recycle loop. Once the throughput manipulator has been put in there, then what you do is you design inventory control system radiating outwards from the throughput manipulator, and these inventory control loops close all the independent material and energy balances around the throughput manipulator. And once you have synthesized the control structure, particularly check for the closure of overall material balance, check for these slow drifting modes that can be there, subtle drifting modes, and if they are there, identify them, close them. And once you have made sure that all drifting modes are closed, all subtle balances are also closed, then you're convinced that you've got a consistent control structure that will take my process to a steady state. Once you have a consistent control structure that will take your process to a steady state, then the next question that you ask is what should be the set points of the inventory controllers that are there in that control system. These loop set points should be chosen wisely. These typically come from economic considerations. Many a times these economic considerations will dictate reactor temperature should be maximum, reactor pressure should be maximum, reactor level should be maximum, product quality should be minimum, and so on and so forth. Many a times these set points are maximum or minimum. For the case where these set points are neither at maximum or minimum, you have unconstrained set points. These unconstrained set points need to be managed wisely. These unconstrained set points can be used to control magic variables that ensure near optimum operation. We're going to talk about that sometime later. As of today, this is enough. I think I've talked enough. We'll end today's lecture. It was not a long one, so I hope you'll be able to see it and appreciate it. Thank you very much for your attention. We'll call it quits. Goodbye.